Now that we have the Kirchhoff laws and the models, mathematical models for resistors, capacitors, and inductors all in place, we're ready to talk about transient circuits. First is to describe what do I mean by the term transient. It's simply something that's changing with time. Steady state has to do with the idea of things having achieved constant values. So if you think back to that capacitor charging problem that I sketched before with the resistor and a capacitor, in these transient problems it's very common to have a switch in the circuit, and that switch will sometimes be labeled with a particular time that's going to either open or close. If this is a voltage V and this is a resistor R and capacitor C, what we can discuss just verbally is what will happen when the switch closes. The capacitor now can have a path for electrons to flow from one plate to the other. Current is going to go clockwise through the circuit, and the capacitor is going to start charging up towards its eventual final value. Well, once it's achieved that final value, there'll be no more currents, no more changes in voltage or current, and so we will have achieved steady state. What I want you to see from the model for the capacitor is what that means. Equals C times d by dt of a constant if we're in steady state, and so we get I equals 0. And that is, if a capacitor is in steady state, whether it has 0 volts on it or some finite DC voltage, that voltage is no longer changing with time, so this derivative disappears, and we get current through a capacitor is equal to 0. It's like an open circuit in the sense that you can have a voltage across the capacitor with no current going through it. Likewise, for an inductor, we have a model that says L di dt is the voltage, and what this goes over to is V equals 0 in steady state. Because, once again, steady state means everything is constant. This I would be a constant value, and so di dt would be 0, and that gives you a 0 voltage. An inductor in steady state is like a short circuit. And you can use these two properties to figure out not only the final values, but sometimes the initial values of the voltage on the capacitor or the current through an inductor. And as an illustration of these techniques, I want to take you through 4 sample problems, 2 each for capacitors and inductors, to show you where the equations come from and to remind you of some of the actual equations that you'll see in your formula book, in your reference book, but to let you know where those equations come from. So first, if we're looking at a capacitor that has some energy stored in it, and so if we say this is a voltage Vc as a function of time, and here's a switch and a resistor. So the capacitor has capacitance C, the resistor has resistance R, and this switch closes at t equals 0. If we set Vc equal to its initial value at t equals 0, then V sub C of 0 would be some set value, say capital V volts. Now what happens when this switch closes is a current will start to flow through the circuit. And now I want to point out to you something very important about our capacitor model, and that is the passive sign convention. Without it, we would get our equation wrong and we would predict something sort of ridiculous, and I'll show you what that is in a minute. Passive sign convention says that the inductor current is C dV dt with positive sign if and only if the voltage on the capacitor matches the direction of the current, like so. So if your capacitor current is flowing from higher to lower potential, then you can write this equation. What happens, as in our present case, the capacitor has a voltage with this polarity, and the current's actually going in the opposite direction. So make this a good if-then statement. If this is the situation, then the linear model reads I is equal to negative C dV dt. And that has to do with the energy flow in the capacitor. Compare with a resistor, where power in the resistor is always V times R, and it's always going to be voltage with plus to minus polarity matching the direction of current flow. For a capacitor, if that capacitor is charging up, the current's going from higher to lower potential. But in this case, the capacitor is discharging, so the current's actually going from lower to higher potential. The capacitor is acting temporarily, in this case, as a source of energy. And therefore, we need to have our power expression, P is equal to VI, match up correctly with the right algebraic sign. So that's where this name comes from. It's a positive sign in the linear model if the capacitor is acting like a passive element. But in this case, it's acting more like an active element. It's delivering energy to the rest of the circuit, and therefore you need a minus sign in the model. Okay, what we can do now is go on and elaborate on that with our Kirchhoff law. The goal is going to be to set up an equation that we can easily solve. In this case, it will be a differential equation. In fact, it will be a first-order differential equation. That's where the title of the first-order transient section comes from. So what we do now is write out the Kirchhoff law with the switch closed. You can actually show that it's a closed switch with two little node symbols like that. And what we need are two different symbols for the capacitor voltage, plus to minus, for the resistor voltage, plus to minus, and here's our current. It's a clockwise current going through the whole loop, and we can just call that I. Since it's the same current for both elements, we don't need a special subscript on that. Now let's do the Kirchhoff law first. If we start at, say, this node and go around clockwise, I bump into a minus sign on the capacitor and a positive sign on the resistor. So I'd write the Kirchhoff voltage law. Minus VC plus VR equals 0. But now what I want is an equation for I. And so I need to substitute my models. Now so far, we've only looked at I is equal to C dV dt as a way of describing the voltage-current relationship for a capacitor. But it's pretty clear we could integrate on both sides and have a voltage that's equal to 1 over C integral of I dt. And you've actually seen this equation before. If you just look at what is the result of integrating a current over a period of time, well, you can find out the answer just looking at the dimensions. Current is in coulombs per second, dt is in seconds, and so if you cancel out the seconds, you get coulombs. And so what we're actually looking at is charge over capacitance, and this is our familiar Q is equal to CV. So again, this might be a way of remembering this form of the model for the capacitor. This is the equation that we want to use now to substitute for V sub C. So if we continue with our Kirchhoff voltage law, we have a minus VC, but remember the passive sign convention? This current is going from lower to higher potential. And the way I wrote the model here was with the positive sign. If I wanted to make this correct with the passive sign convention, I need a negative sign here and a negative sign throughout here. And so for purposes of substituting into our equation, this is what I need for the voltage expression for the capacitor, and there's the crucial minus sign. For the resistor, it's much easier, just Ohm's law. V sub R is equal to R times I equals 0. And now if I differentiate this expression once with respect to time, it clears the integral. And if I simply divide through by R and rearrange terms, I get a standard differential equation, di dt plus 1 over RC I equals 0. Now that's the differential equation we want to solve, subject to the initial condition, which we know from having looked originally at the circuit, Vc of 0 is equal to V. Okay, so now it's just a matter of solving an equation that should be very familiar to all of you, first order differential equation with constant coefficients. And so let's just copy down that differential equation. And I'm going to suggest to you that the solution to this is an exponential. If you need to go through the derivation of that, you can do that as a side exercise. But this is by inspection. And when you're in the middle of your exam, you might see equations like this that you just recognize the solution, and that's okay. All you have to do is write it down. If you want to, you could verify by substitution that if I just substitute this expression in for I in both of these terms, I get an identity. And what this tells us is that if I is an exponential, then di dt is also an exponential. It just differs by the coefficient. If I differentiate e to the st with respect to time, I get s times e to the st. And that's really just s times my original I. A e to the st here and here. Multiply s times I and you get this expression. So that allows us to rewrite our equation as s times I plus 1 over RC times I equals 0. Solve that for s, because we can assume the i's drop out. The only mathematical problem would be if I is equal to 0, you can't divide by it, but this would be a pretty boring problem if I were 0. So this is the only case we're really interested in. What we can do now is come back to the equation I of t, a e to the minus t over RC. Now all we have to do is figure out what is this constant A. And we can get that from the initial voltage. V of 0 is equal to the resistance times I of 0, and we know that because the voltage on the capacitor is the same as the voltage on the resistor. They happen to be in parallel. And this is, in turn, V volts. So now all we have to do is substitute from our model, from our solution here. I of 0 is A e to the 0. So I of 0 is A. E to the 0 evaluates as 1. And now we can solve for our constant. A is equal to V over R. What we get, and I can put this up here, is that I as a function of time turns out to be V over R times e to the minus t over RC. This is an exponential decay. And it's the type of exponential decay you see in a lot of physical problems, a lot of engineering examples. But what we can do is look at a sketch of that and help you remember what the RC actually is telling you about this circuit. If this is my current, V over R e to the minus t over RC, and we sketch this as a function of time, what that says is at t equals 0, my current is V over R. And if I wait long enough, for a very large time, e to the minus infinity goes to 0. So eventually the current's going to go all the way down to 0. And in the meantime, it's going to follow an exponential decay shape. Another way of writing this expression, though, is to say it's some initial value V over R times e to the minus t over, and tau is called a time constant. One of the neater interpretations of the time constant is that if you look at the initial slope of this curve and just draw a tangent and continue at that rate, at a constant rate equal to the initial rate of decay, then your entire current would decay away in tau seconds. So that's a nice interpretation. Tau has SI units of seconds. This also tells you that after 2, 3, 4, 5 time constants, your current is virtually zero. It started off at some reasonable large value, but after 5 time constants, it's pretty much disappeared. And so that's what we usually call, in circuit analysis, the transient period. You say that it ends after 5 time constants. Well then, that's the discharge of a capacitor that originally had some energy stored in it, and the mechanism for letting that capacitor discharge was to have current flow through a resistor. Previously, though, I drew a picture of a voltage source charging up a capacitor through a resistor, and that's a companion problem that what I want to do now is show you essentially the result. I'll give you the beginning steps of the derivation. You can fill in the steps as you wish, but the result is very similar, and for that we just need a battery, resistor, switch, and a capacitor. What we have to do in this case is set the initial condition on the capacitor, V sub C. V sub C at time equals 0 is now assumed to be 0 volts. So what we're saying is that this capacitor is initially uncharged. What we're going to do is close the switch at t equals 0 and let the capacitor charge up through this resistor R. Think back to the steady state analysis and also think in terms of node voltages. We'll have a current in this circuit as long as there is a potential difference across this resistor. But when the current disappears, we've achieved steady state, so there'll be no more current. Remember, I is C dV dt, and so when this capacitor voltage becomes a constant, the current disappears, and there'll be no potential difference across the resistor. The capacitor will eventually charge up to V volts. So what we can do is put that as a final condition using t equal infinity and say that that's going to be equal to V volts. Now, one habit I've gotten into over the years is distinguishing between V, the unit, and V, the symbol. That's where these square brackets are very handy. So you see a V in square brackets, that's units of volts. This is a variable V. Okay, well, what I want to do is the same basic setup, and it's so similar I'll step through it fairly quickly. The Kirchhoff voltage law, going around this loop clockwise, minus V plus V sub R plus V sub C equals 0, minus V plus R times I, and now we need a plus sign. And you should remember that's from the passive sign convention. The current that I'm describing in this equation is the current going clockwise through the circuit, and it's going from higher to lower potential. The capacitor here is acting like a passive element, and so I use the positive sign in my model. Well, once again, we differentiate to clear the integral sign. And we wind up with pretty much the same differential equation. The time constant is going to be the same. The only thing that's different is that our initial and final values dictate that we go back and change a slight variation on the constant. What you can do is continue the math and substitute in the initial and final conditions, and you'll find that what you get is a current that actually decays. It has some initial value, e to the minus t over RC. But if what we really want is the capacitor voltage, then we're going to have to apply this model to the results of this differential equation. So when you integrate this current and you set the initial and final conditions, what you wind up with is an exponential. Has the same basic form here, but it's subtracting off from a constant. And instead of being an exponential that decays from a constant value towards 0, this is a voltage that builds up from a 0 value to an eventual value V. Look at what happens at the limits. For t equals 0, this exponential term disappears, and you've got V sub c is equal to V. At t equals 0, e to the 0 goes to 1. 1 minus 1 disappears, and this whole term becomes 0. And I knew that had to be the case because my initial value, Vc of 0, was equal to 0. And now if we look at the final limit, t equal infinity, e to the minus infinity goes to 0. That's the term that disappears. And so Vc of 0 turns out to be 0. Vc of infinity turns out to be V, just like it's supposed to. And if we look at the sketch of this, we'll also see how the time constant comes into play here. For the capacitor voltage, for a charging capacitor, we've got an eventual steady state voltage of V, but we have to wait an infinite amount of time for it to actually get that large. Vc starts at 0, so this is Vc of t, starts at 0 and builds up, getting closer and closer, asymptotically approaching the final steady state value. And once again, the time constant comes in. If we look at the rate at which this curve is increasing, the initial rate would mean the capacitor would completely charge in just tau seconds if it could continue to charge at that initial rate. But since the rate that it's charging is constantly slowing down, it takes forever for it to completely charge. And once again, this time constant t for an RC circuit is t is equal to R times C. Well, the next two circuits I want to show you are for resistor-inductor problems, with the inductor initially storing energy and discharging or de-energizing through the resistor, and then the companion problem, which I will show you the setup and the solution, and the intermediate steps are very similar to what we've just seen for the capacitor charging. One reason that I prefer this term energizing and de-energizing is just to remind you that the inductor doesn't store energy with separated charges, so it would be misleading to call this an inductor charging or discharging problem. Instead, it's the inductor is storing energy in the form of magnetic fields, and so maybe it's initially energized. And the way we can do that is to have, and let me be careful about the directions here, an initial DC current source connected to an inductor. Okay, and then we have a resistor over here. And what I need to arrange for here, and there's a practical reason for this, I need a switch that's going to smoothly switch from connected to the source to being connected to the resistor. And so I'm going to use a switch that kind of looks funny. It's supposed to indicate that here is the moving element of the switch, and as the switch slides over from this position to this position, there's a continuous contact. If we just used a regular two-pole switch, then there would be an instant of time between switch in this position to the switch in this position where an energized inductor would have energy stored and no way for that energy to be released in a controlled way. So you'd have tremendous arcing problems, and that's just a safety hazard. So whenever I show this circuit, I always include the this sliding contact switch to illustrate. Now, the whole point is, when the switch is in position A and we leave it there for a very long time, then this inductor is going to have I amps through it. So what I can say is at t equals 0, I slide the switch all the way over to position B, and now the current that was going this way through the inductor is now the current that's going to be energizing this loop. Now that I've gone through all of that and justifying it, what I want to do is show you the T after zero circuit. It's a lot simpler. So here I have the inductor, the resistor, and the current. Once again, our goal is to set up a differential equation for this current. We know that the initial value, I of 0, is equal to I. And if you just think about the power equation for the resistor, says that as long as there's current through this resistor, power for the resistor is I squared R, and that's positive. So that means that power is going to be dissipated out of this circuit, and there's no way for more energy to come into the circuit. So we start off with a certain amount of current. That energy is going to be dissipated by the resistor, and eventually that current's going to decay away. So what we can do is just predict intuitively this current is going to decay exponentially the same way that the capacitor voltage did. And once again, I'm appealing to the analogies between the capacitors and the inductors. Just as we had passive sign convention for the capacitor, we've got passive sign convention for the inductor. In this case, with the current going from lower to higher potential, the inductor voltage is minus L di dt. For the resistor, you always have R times I. So now we can set up our differential equation from the Kirchhoff law. Start at this node, go around clockwise. Minus V sub L plus V sub R equals 0. Minus L di dt plus R times I equals 0. And now we get our first order differential equation that reads di dt plus R over L I equals 0. This is the same equation we had before, it's just the constant has changed. The time constant is a little different. So what we have to do now is the solution to that equation is again an exponential. And so we have if di dt plus R over L I is equal to 0, this tells us that I equal to a e to the st is going to be satisfied by Si plus R over L I equals 0. The S turns out to be negative R over L. And the initial value of current we can read right off of the problem statement. At t equals 0, I is equal to I amps. So we can quickly come up with the final solution is capital I times e to the minus R over LT. And if you put that into the time constant form, e to the minus t over tau, where tau in this case has to be L over R. Now this gives me an opportunity to talk to you about the units of inductance and resistance and where this comes out to be units of seconds. It's a handy trick from the linear model. If you remember, V is L di dt. Then you think of that as inductance is a ratio of voltage to rate of change of current. So a unit of inductance would be units of volts divided by amps per second. Or if you like, a unit of Henry is a volt second per amp. And now if we put Henrys up here, volt seconds per amp divided by volts per amp gives you units of seconds. This is going to possibly be very useful in checking the dimensional consistencies, making sure that you haven't made any mistakes in your calculations. Similar expression for a farad. You can go through the same kind of analysis with the model for the capacitor and convince yourself that a farad is an amp second per volt. And that's why R times C gives you units of seconds for time constant. That bit is just an aside about the units. Okay, so at this point we've established that the current in that inductor is going to decay exponentially. It's going to follow a time constant, and in fact we could do the same sketch that we had before for the capacitor voltage. We have I decaying away, and of course the time constant would be somewhere right about in here. If we decayed at that constant initial value, would decay away completely in tau seconds. Now you have a companion problem, which is what happens when you connect a current source to an inductor through a resistor. And what I want to do now is just show you the circuit and give you the result, because it's very similar to what we did before. This says, and of course I'm showing symbolically with just the single pole switch. If I wanted to be more careful about it, I'd use another one of those sliding contact switches. But to get to the point quickly, I have a current source of I amps. If I close this switch, then eventually this inductor is going to have I amps going through it. But if initially the current in this inductor is equal to 0, it's going to take a certain amount of time for that current to build up. So just appealing to your intuition now, what we have is a capacitor charging situation to think back to. This inductor energizing up to a full current of I is going to follow the same basic physics, because after all the basic VI equations are the same, derivative of one relating to the value of the other. If this is a plot of the current in the inductor as a function of time, it has this exponential increase behavior. After tau seconds, it will have achieved its final value if it were still increasing at this initial rate, but since the rate is constantly slowing down, it takes forever to get there. And what I predict from the full analysis of this problem is that you would get exactly that form with tau equal to L over R once again. So you can see now by this past couple of examples with capacitors and inductors, there's an awful lot that's similar between the two. What inductors do with currents, capacitors do with voltages. The equation for the voltage-current relationship with the inductor is just the same as for the capacitor. You just exchange the roles of V and I and exchange inductance for capacitance. Throughout these last four problems, you've seen the power of applying the Kirchhoff laws and these mathematical models to varying situations. And all you'll have to do is think through the model, apply it to the steady state conditions especially, to come up with initial and final values, and just keep your head in these calculations, where it all boils down to fairly basic concepts. The Kirchhoff laws are charge conservation and energy conservation. The linear models for the inductor, the capacitor, and the resistor are all just simple equations, and it really is a matter possibly of keeping your minus sign straight. So be real careful with your passive sign convention. Next topic to move on to is AC signals, and then we'll be looking at how AC elements are handled in circuit problems. An AC signal, as you may know, refers to alternating current. So if this happened to be a current, it would be alternating between positive and negative values. The nomenclature now applies to an AC signal, whether it's a voltage or a current. You have this basic sinusoidal oscillation. Vm is called the magnitude or the amplitude. You'll see it referred to in both ways. Capital T is the period, or the amount of time it takes for the waveform to cycle through all of its intermediate values, starting at, say, the peak and going to the next peak. It takes capital T seconds to proceed that far in the waveform. It doesn't have to be from peak to peak. You can go from this zero crossing to this zero crossing. You just have to wait and make sure that you get the next zero crossing with a positive slope. So you go from this point to this point, and that's capital T seconds. That's measured in seconds. Of course, voltage amplitude would be measured in volts. F is called the frequency. tells you how many cycles per second do you go through. It's in hertz. And the first relation between these is that frequency and period are just inverses of each other. Now this letter omega, not to be confused with energy W, you have to be real careful. In my handwriting, a W gets a little serif here. It's even more important if you, it's more clear if you put W of T. Now that's clearly energy as a function of time. Omega is always a constant. But letter carefully so you don't confuse yourself. This is omega. It's 2 pi times f. So in turn that's 2 pi divided by t. This is measured in units of radians per second. It's called the angular frequency. So you have to be a little careful in problems. If you're given the frequency in hertz, that's this number, f. If you're given the symbol omega, you have to remember that's 2 pi times f, and it has to do with measuring angles in radians as opposed to measuring in degrees. Phi is a phase angle, and I'll elaborate on that in the next sheet. When you put all these factors together, you wind up with this typical sinusoidal waveform, and it's referred to as a sinusoid. A lot of authors, and it's very conventional to use the cosine function. You could just as easily use the sine function for this. But notice how all of these factors play a role in defining this function as a constant, as a function of time. What I want to do next is to describe to you a little bit about what phase shift means in terms of AC waveforms. Phase angle is usually measured in degrees, but if you think of it as measuring where in the sinusoidal cycle you are, that's a very useful way to think through it. The best thing is to look at what phase shifts do to the basic cosine waveform. Here we have with a phase shift of 0, and in fact in each of these you can imagine that we're looking at something like I of t equals some I magnitude cosine omega t plus, and little phi here is the phase angle symbol. It's not to be confused with capital Phi, which we used for magnetic flux. Lowercase phi, you don't put the serifs on the top and the bottom. So for a phase angle of 0 degrees, look at the expression. If you put a 0 here, that means that when time is equal to 0, you have a maximum current, and so your peak occurs right at t equals 0, right at the axis. If the phase shift is a small positive angle, and this illustrates about a 20 to 30 degree positive phase shift, look at what's happened is that the origin of time has shifted over to the right with respect to where the peak of the waveform is. Now, you could also think of that as the axis staying fixed and the cosine has slid over to the left a little bit. Personally, I prefer thinking of the waveform as being the fixed object, and then whether my phase shift is positive or negative takes this time axis and shifts it over to the right or to the left. I think it's intuitive from the number line. Positive things should be motion to the right, negative things should be motion to the left. So compare that with a negative phase shift. If you started off with the time axis here and you shoved it over to the left a little bit, that would be a small negative phase shift. So I hope that helps you in sorting out problems involving actual values for phase angle here. There's an even better way of resolving that with a notation called phasors, which we'll get to in just a few minutes. Before I talk about phasors, though, there are a couple more just basic calculational items to know about AC waveforms. One is the average value. If you have, say, a typical sine wave oscillating about 0, and this is V of t, V average for this waveform is equal to 0. If, however, you've got a case where here's the 0 volt level, and what you've got is an AC signal riding on top of a DC signal, and let's say this is maybe a 3-volt line, and we've got perhaps a half-volt amplitude waveform. So V of t here would look something like this: 3 plus 1/2, and I'll just go ahead and call it sine of omega t since I started off at the 0 value at t equals 0. What I get for the average value here is equal to 3. And if you have a sketch of the waveform available, it's real easy to see. You just take what is the magnitude of the maximum, what's the magnitude of the minimum, and split the difference between those, because this is a symmetric waveform. It's alternately going above the 3-volt line, below the 3-volt line, and so on. And of course, this DC level shift can be anywhere at all. It could be a negative value. So that's the idea of average value. Effective value, or RMS value, is a little bit different. What you're looking for is a value that, let's see, one of the modifications to the voltage source symbol that you see in some books is you include a little AC sine wave symbol to say this is a voltage source, but it's oscillating sinusoidally. And in terms of how much power is being dissipated in this load resistor, there is an effective DC, and let me emphasize that by using a battery, a DC voltage called VRMS that would have exactly the same effect on the load resistor. And the fact that it has the same effect is where this effective value comes in. So if you're looking for VRMS or V effective, they are the same number. Now, the way you calculate the V effective is suggested by the alternate name. RMS stands for root mean square. What you do is you take the square root of the mean value, the square root of the mean value of the squared quantity. So definition of VRMS, it's a little on the elaborate side, but there's a simple equivalent version of this. What you would do is take your sinusoidal waveform, so this V of t, for instance, take this voltage, square it, integrate over one cycle, divide that result by t, and then take the square root of all of that. And you can see dimensionally it works out. This has units of seconds, dt has units of seconds, so the seconds cancel out. You've got the square root of volts squared. What's real nice is that for AC waveforms, this turns out to be 1 over square root of 2 times the magnitude. For specific case where the average value is equal to 0. So if I knew the magnitude of this waveform, then I would be able to calculate the RMS value simply by multiplying by 1 over square root of 2. Now, RMS plays an important role in AC power, which is a subject that we'll get to later on. Next, though, I want to talk to you about phasor notation. It's a mathematical representation of a sinusoid that allows our equations to be very simple form. Equations for AC circuit analysis could be very, very complicated. If there are all these sines and omegas and phis floating around, and you have an expression like that for every voltage and current in the circuit, pretty soon your simultaneous equations are really getting out of hand, just clumsy mathematically. The phasor notation allows us to handle the sine functions of time as constants, and then our equations start looking very similar to DC circuit equations. So that's the motivation, the rationale for talking about phasor notation. It's going to require a little bit of an excursion into complex algebra, which I think at this point is just going to be additional review. You've seen all this before in some math course before, or in your circuits course. The basic idea of the phasor is that it's a vector in the complex plane. It's considered fixed for circuit analysis purposes. But if you ever want to relate it to the real world, it rotates at omega radians per second to duplicate the effect of a sinusoid at omega radians per second. Now, what does all that mean? If I have the complex plane, where the real part is the horizontal axis and the imaginary part is the real axis, and I just draw a vector in that complex plane, the only thing I'm allowed to do for a real measurement is to look at the projection onto the real axis of that vector. And now if I let that vector start rotating at a frequency of omega, then you can see the projection. If I rotate to a point where the vector is pointing up here, then the projection is at this point. If the vector rotates over here, the projection is to a negative value. And so in fact, if I look at my pen here as the phasor rotating, imagine that it's rotating around. Now I have to think through this. I want it to go counterclockwise as you're looking at it, so I'll go clockwise. And as this pen is rotating around and around, follow the tip of it. But I'm going to continue that rotation, but now I'm going to do it in a plane, so that now all you can see is the tip. And the tip is oscillating back and forth. If I just project the tip into space, it's going back and forth like this. It's tracing out a sinusoidal waveform in space. And that's the idea, linking together this phasor, which is the complex vector, with the actual real physical thing is the projection onto the real axis. And as this phasor rotates round and around this unit circle, the projection onto the real axis alternates between negative, positive, negative, positive. So if I just track the location in terms of real numbers, the location of the tip of this arrow as it rotates around, that tells me, well, to start off with, if this was my initial point, I'm at a little less than the maximum, because the maximum would be if the phasor is pointing directly along the real axis, and I'm going to continue to decrease. So the part of the cosine function that I'm in is about there. And as I continue, let's say this is t equals 0, this is at t1. Okay, there would be t1. Let's go around to, say, t2. At time t2, I would be in a region where the projection on the real axis is negative, so I'm somewhere down in here, not quite at the minimum. And so you see how this works. As the phasor rotates around counterclockwise around the complex plane, the projection onto the real axis is alternating between positive and negative values, and that's duplicating our sinusoid. Now if this is a voltage, and our voltage V of t is V magnitude cosine omega t plus phi, the way I write down this phasor, in handwriting you have to, it's a bold-faced letter in text, and for a bold-faced handwritten letter you just do a double stroke for the whatever is an appropriate part of the letter to double up. So for the voltage, it's this left-hand side. You double that up to make that a phasor. The phasor is nothing more than the magnitude and the phase angle. And the advantage here is that we've eliminated all of the common expressions. Everything in our circuit is going to oscillate sinusoidally, the same cosine function, the same omega. But the important things for any particular element or source are the amplitude and the phase angle. So this is how you get a phasor from a sinusoid. In using phasors in circuit analysis, we're going to have to be able to add them, subtract them, some cases multiply together, do an operation called conjugation. So to set the stage for all of that, I want to review in just one sheet all of the algebra complex numbers that you need to remember for this test. Starting off with the basic complex number, which has two real number components. There's the real part and the imaginary part. And we can sketch this on the complex plane, real, imaginary. If this is A and this is B, then the complex number is actually a point in the complex plane. Our phasors are going to be vectors pointing to that point, but just to keep the notation a little simpler, we'll think of it as just a single point. Now what we might want is the rectangular coordinate version, that's this version, or we might want the polar coordinate version, which is a magnitude, call that r, and an angle, which let's call that theta. Okay, so what I can do is translate this into r at angle theta terms. R from the Pythagorean theorem is just the square root of a squared plus b squared. And from the basic right triangle, you've got the angle is the inverse tangent of the imaginary part over the real part. Now there's another way of getting the magnitude, uses what's called the complex conjugate. To form the complex conjugate of a complex number, you just replace all j's with minus j's. So C star in this context is A minus JB. Another way of writing the magnitude is to say that that's equal to the square root of the conjugate times the number itself. And you can see where that works out, because in this expanded form, you can tell the cross terms are going to cancel out. The minus JBA and the positive JBA terms are going to cancel, and that leaves you with a squared, and then minus j times plus j. I forgot to mention to you that j is equal to the square root of -1. That's the basic definition of the imaginary unit. In circuit analysis, we use j for the square root of -1 because I is already reserved for current. Now the fact here is that j squared is equal to -1. So if you have negative j times positive j, that gives you a negative j squared, and that makes a positive 1. So you wind up with, once again, the square root of a squared plus b squared. Okay, finally, if you want to add and subtract complex numbers, you simply treat them like vectors. Here the real and imaginary parts A1 and B1 correspond to the complex number C1. C2 in turn is equal to A2 plus JB2. And all I did to combine these was to combine real parts and combine imaginary parts. If you want to multiply them, the best idea is to convert over to the polar form first. And then multiply according to the rule that says the amplitude is just the product of the amplitudes. The phase angle is just the sum of the phase angles. Now with that basic foundation in complex algebra, we can go ahead and talk about the most useful application of phasors in AC circuit analysis, and that's converting to a mode of description so that we can write out Kirchhoff laws, voltage laws, current laws, set up all the circuit analysis techniques that we had for DC circuits using an equivalent concept in AC circuit analysis called the impedance. So let's start by describing what an impedance is. The concept of impedance is very similar to resistance. In a DC circuit, you have a resistor that has an Ohm's law that says V is equal to R times I. For an AC circuit, the equivalent concept to resistance is impedance. And so what we want to do is set up a ratio of voltage phasor to current phasor. And this is strictly analogous to resistance is equal to V over I. The only thing is, for an AC circuit problem, we have to go over to the phasor notation. Both of these are going to be potentially complex numbers, and therefore impedance is a complex number. It has real and imaginary parts, and they're given names, R and X. R is called a resistance, just as we had before. And X is referred to as reactance. They both have units of ohms. Now, what we need to do is look at what are the impedance formulas for resistors, capacitors, and inductors. For a resistor, Z sub R is simply equal to R. We've already got the Ohm's law. It says this is a real number divided by a real number, so it's not complex at all. It doesn't have this imaginary part. The impedance of a resistor is purely real. It's a pure real number. For a capacitor, Z sub C is 1 over J omega C, or if you want to define that as J times X sub C, where X sub C is equal to negative 1 over omega C. This is a pure imaginary. Now, where that came from is the fact that 1 over J is equal to negative J, and you can prove that because negative J squared is equal to 1, and that comes from the basic definition that J is the square root of negative 1. You can prove that out for yourself. So we have two of our impedances already, resistor and capacitor. For the inductor, Z sub L is equal to J omega times L. So in turn we can call that J times X sub L, where X sub L is equal to omega times L. Now the whole idea is to go from an AC circuit with defined sources with resistors, capacitors, and inductors. And if I know that AC source frequency, I can convert the entire circuit over to a phasor and impedance model and then apply exactly the same circuit techniques that I used for DC circuits. The only thing is now I have complex numbers to deal with, and that just makes the arithmetic a little bit tedious and nothing more. It's conceptually exactly the same as we talked about already for DC circuits. So let's take a typical problem and say this is a given voltage waveform, and we have a resistor here and a capacitor, resistor and inductor, and let's make this a capacitor and a resistor. Complete the circuit. Okay, and we would have an R1, let's call this C1 and C2, L, R2 and R3. Someone would have to tell us about this AC waveform. It's got, say, a 5-volt amplitude, follows a cosine law. I'll show you a pretty typical way of describing frequency. 2000 pi t plus, say, 40 degrees. Now let's extract all of those components that we talked about before. In this case, the amplitude V sub m is equal to 5 volts. The frequency, and this is the point I wanted to make, is everything multiplying time t is the frequency omega. So omega is 2000 pi, in turn is equal to 2 pi f. So if you wanted the frequency in hertz, that would be 1000 hertz. The phase angle is phi, is 40 degrees. But now remember how we form the phasor is just to take the amplitude and the phase angle part. So if we make this V phasor is equal to 5 at angle 40, the impedance for each of the resistors is just the resistance R1, R2, R3. But now we need to use the frequency, the angular frequency omega of 2000 pi to calculate the impedances for C1 and C2 and L given the impedance models and given the values of C1, C2, and L. So let's do that. We'll say ZC1 is equal to 1 over J omega C1. ZC2 is 1 over J omega C2. and Z sub L is J omega L. Now with all of these substitutions, we're going to come up with a different circuit, a phasor equivalent circuit or an impedance model for this circuit. And I want to show you what that would look like. You can use just the generic symbol for voltage source, because if you label it with a phasor, it's then pretty clear that you're talking about a phasor equivalent. Okay, and you have R1 is a numerical value of the resistance. That becomes the impedance for that resistor R1. For C1, we're going to put in the complex number, or the pure imaginary number, 1 over J omega C1. And so on around the circuit. We have a resistance R3 in this box, an impedance of J omega L in this box, and then down this branch we've got a 1 over J omega C2 and an R2. So far we've just substituted the phasor equivalent and the impedance equivalents. Now the question is, what do you do with this? What you would do is simplify this circuit using series and parallel combinations. And that's a key concept, is that in series connected impedances you have the same sum rule we had for series connected resistors. If you have capital N impedances all in series, you just add them up algebraically, remembering to group the real and imaginary parts. You come up with a complex number equivalent here. For parallel connected impedances, you take the inverse of the sum of the inverses. So with numerical values substituted all along here, what you would do is take one grand total impedance for this branch, a grand total impedance for this branch, combine those two in parallel to come up with a single impedance for this whole network, and then add R1 to that. Then what you would have is a straightforward exercise in the Ohm's law. It says I've got a ZEQ now. That's the impedance equivalent of this entire network of resistors, capacitors, and inductors. And from that I can easily calculate the current, because just as we have Ohm's law, V is equal to Ri, we've got the AC equivalent of Ohm's law, V is equal to Z times I. And I would calculate the I in this circuit with V phasor divided by ZEQ. Now you have a number of examples of this in your review material, and this is the kind of thing that you need to practice and practice and practice, just to make sure that you don't make careless mistakes like 1 over J equals minus J is the correct way to do it. If you forget that and you mess up the minus sign, that's going to throw off all your calculations. So one thing I would recommend to you is go to the review materials and practice a lot of these AC phasor problems. While you're going through those problems, keep in mind what I've got on this sheet is that the solution techniques that we had for DC circuits all apply to AC circuits as well. So you have the loop current technique in its phasor form. You've got node voltages. You've got the Thevenin and the Norton equivalents. Superposition also applies, but again, I remind you that's really not a very practical solution technique. And the others that we talked about, the point here is that as soon as you translate your AC circuit into phasor form for voltage and current sources, and you replace all the components with their equivalent impedance, then you can attack those problems exactly the same way that you attack the DC problems and come up with reliable results. You should use the Kirchhoff laws to check your results, and just remember, of course, it's for Kirchhoff's voltage law, it's the sum of all of the voltage phasors around a loop. For the current law, it's the sum of all of the current phasors. So that means you can't just take the amplitudes of the current phasors and add them up to 0. It's the amplitude with the corresponding phase angle. It's analogous to doing force vector diagrams. You have to remember all of those phasors are vectors in the complex plane, so add them together as you would add together vectors. I mentioned that Thevenin equivalent applies to AC circuits. And so if we have an AC active network, and we have an open connection to that network, what we can do is come up with an equivalent V Thevenin phasor and an equivalent Thevenin impedance. It's Z Thevenin. And now we ask the same question again, and that's if I have a load impedance. Now let's call this Z sub L is equal to RL plus JXL. And I want to attach the impedance that has the correct values of R and X to achieve maximum power transfer. Then the question is, what do I attach here? And it turns out that if you attach an R Thevenin and then an X value that's opposite of the Thevenin, then you get maximum power transfer. And this is assuming that Z Thevenin is equal to R Thevenin plus JX Thevenin. Now I've got Z load is equal to R Thevenin minus JX Thevenin. And you notice what happens. These series connected impedances add together, ZEQ, gives you just a pure resistive load, equivalent load, if you include the Thevenin impedance and the load impedance together. The imaginary parts cancel out. And we're going to see in just a minute the imaginary parts represent power that's trapped within the components. It's the resistive part of the power that delivers sound to speakers and delivers force to motors that are turning. Anytime you have a non-zero reactive part, that means you're losing a little bit of your energy to trapped energy in the elements. So to get maximum power transfer, you want to get rid of the X part, and you do that by attaching not the Thevenin equivalent, but the complex conjugate. That's what this represents. So the net result here is to get maximum power transfer for an AC circuit. If you know the Thevenin equivalent, what you do is attach a Z sub L that's equal to Z Thevenin conjugate. And that's a little different from what we did with real resistive circuits, where to get the maximum power transfer to the load, you attach the load resistance equal to the Thevenin resistance. For AC circuits, you make it the load impedance equal to the Thevenin impedance conjugated, so that you get rid of that imaginary part. Okay, let's talk for a minute about complex power. How power appears in AC circuits is the same way theoretically as for DC elements. You have a power that's equal to a voltage times a current. And if these are AC voltage and current, then they each have their phasor equivalents. Now the phasor equivalent of this equation is not just V phasor times I phasor, but for a very similar argument to what I just made, you multiply by the conjugate of the current. This is where the concept of effective value or RMS value comes into play in power calculations. So the point is, if you want to get the total power in an AC circuit element, you have to multiply the effective value voltage phasor times the conjugate of the current phasor effective value. That gives you a complex number. It has real and imaginary parts. This is called the power, or the real power, and Q is called the reactive power. Okay, just nomenclature and unit terminology. All of these are power concepts, and so they can all be ultimately related back to the watt. Problem is, we don't want to use the unit watt for everything. It would be a little confusing. So when we're talking about total power, S, that's in volt amps. When you talk about real power, or just shorten that to power, that's the power in watts that we're accustomed to from DC circuits. The Q, the reactive power, has a new special name. It's volt amps reactive. And so if you hear someone referring to a 10 volt amp reactive element, then you know immediately that that's from the units, you know that that's the imaginary part of a power. Now, to keep things straight, there's a nice graphical analog to this expression, S equals P plus JQ. It's called the power triangle. And the power triangle simply plots real power horizontally, reactive power vertically, and the hypotenuse of that triangle turns out to be the total power, S. And you can see if this is in the complex plane, if this is a real part, this is an imaginary part. It's a simple application of the Pythagorean rule. It says the square root of P squared plus Q squared gives you S. So we can label this hypotenuse as S, this real leg as P, vertical leg as Q. Then there's an angle that comes in here, theta, such that the cosine of theta tells you about the relationship between the total power and the real power. The sine of theta tells you about the relationship between S and Q. So cosine theta is given a name of power factor, or PF. Sine of theta, since it has to do with reactive power, is given the term RF, or reactive factor. And the one that you're probably going to see most often in your exam questions is power factor. So now the question is, how do you use that to interpret some problem statements, and what does that have to do with practical situations like motors, generators, and other kinds of power applications? Well, the power factor tells you if it's a positive or negative power factor. It tells you if your load is more of a capacitive type load or more of an inductive type load. Okay, and this gets into the topic of leading and lagging power factors. Well, to illustrate, if you think about the phasor diagram for a capacitor, its current phasor is going to be ahead of its voltage phasor by 90 degrees worth of phase shift. So if you have a capacitor phasor diagram, here's the real axis and the imaginary axis. If we just arbitrarily say, okay, here is the voltage on the capacitor, the current is going to lead the voltage by 90 degrees. So I go 90 degrees in front, and always these angles are positive counterclockwise around the complex plane. This would be the location of the I phasor for the capacitor, and that's a 90 degree phase shift between the two. Okay, for an inductor, it's very similar, that we're going to have a current lagging behind the voltage, or you can turn that phrase around and say voltage leads current, or current lags voltage. It's just a matter of keeping track of who passes a certain point first as you're rotating around counterclockwise. If V comes before I, let's say you're an observer at this point and you're noticing these two phasors, they're locked together with a 90 degree phase shift, but they're rotating in this counterclockwise direction. The V phasor passes first, and then 90 degrees worth of phase shift later, I passes. So you'd say V is leading I, or as it says here, I lags V by 90 degrees. Now, there's a nice little mnemonic to help you remember that. if you just go over to the alternate notation for voltage, which is to say E. Now, in electrical engineering, we generally don't use E for voltage because we like to use E for electric field, but throughout history, physicists have used E quite a lot for potential and potential difference. And so if we make the same change here, labeling both of these voltage phasors with E's, what we can do is insert the symbol representing the element, and this suggests a little mnemonic, E-L-I, you think of as a person's name, Eli, and the word ice, I-C-E. This little mnemonic grew up in the times when people actually had icemen coming to their houses delivering ice. So if you don't know what an iceman is, you can look up or ask a grandparent or something. At any rate, Eli the Iceman is a mnemonic. You can either take it or leave it. If you would rather just remember the rules, there they are. But if you're like me, a picture helps a lot. And so that's our friend Eli the Iceman. Now, what this is going to help you with is remembering in the power triangle that a lagging power means that the current is lagging the voltage. Leading power factor means that the current is leading the voltage. And you'll only ever be given the power factor in terms of a number, like power factor of 0.9 corresponds to a power triangle where the angle theta has a cosine that's equal to 0.9. But as you know, the cosine function is an even function. So cosine of a positive angle is the same as cosine of the negative angle. And it's that positive or negative that tells you whether it's leading or lagging. So the problem statement will have to include the terminology power factor leading or power factor lagging. And the phasor diagrams I just showed you should help you remember which is which. Now, the last topic within the AC circuits that I want to talk about is frequency response. As you notice, these impedance models for the capacitor and the inductor involve the term omega. And that means that those impedances are sensitive to the value of frequency. And this is a very useful, very powerful phenomenon. It allows you to select signals with different ranges of frequencies for further processing. So what you do is look at, in frequency response, you're generally comparing an output parameter to an input parameter. In most of your examples, you'll see output voltage compared to input voltage. And you consider that as a function of frequency. So the idea is that you have some kind of circuit down in here. At 2 points, you're identifying as the input some input voltage. And then at some point in the circuit, you're probing the output with a voltmeter or an oscilloscope or some other measuring device. And what you do is set up a ratio of V out divided by V in. And that's defined to be an amplitude function of frequency and a phase angle function of frequency. Now, if you think about it for a second, the voltage phasor has amplitude and phase angle parts. The voltage phasor here has an amplitude and phase angle. So the ratio of those two, logically, would be in this complex form, the polar notation, amplitude at a certain angle. And what we're going to explore now is how do these amplitude and phase expressions take shape for low-pass filters, for high-pass filters, for capacitor, resistor, inductor circuits. To introduce the terminology, here's what an ideal low-pass filter would do. Looking at a plot of A of omega as a function of frequency omega, up to and including some special frequency omega naught, I would have a perfect duplication that the output would be exactly equal to the input. This is 1.0, no loss of voltage at all. And when I get above that frequency, I get no output at all. And so the low frequencies are being passed through from input to output. Higher frequencies are being blocked. And likewise for a high pass, at least ideally, would look like this. Starting off with frequency of 0, going up to higher and higher values. At some intermediate frequency omega naught, above that frequency you would pass all signals, and below that frequency you would block. So this is the value of 1.0. And keep these ideal pictures in mind when we talk about the actual first order filters made out of resistors, capacitors, and inductors. All we need to understand these circuits is the basic impedance picture and the Ohm's law in its AC form. And in fact, what I'm going to use is the voltage divider that I've introduced earlier with DC circuits, but now I'm going to show you the voltage divider in an AC context, and that'll help us derive the behavior of this filter. This is called a first order filter because if you went back to solve it as a transient problem, it would have a first order transient response. But now we're more interested in how does this circuit respond to different frequencies as I take the input sinusoid, compare it to the output sinusoid. So you have to imagine that you're looking at this on an oscilloscope. And then let frequency increase. Start at 0 frequency and increase through larger and larger frequencies, and ask ourselves what happens to that output waveform. Well, to figure this out, what I want to do is go over to the phasor form, Vn. I have an impedance R and an impedance for the capacitor. Let me express that as 1 over j omega c. And now we have an output voltage. Well, if it's true that I can handle this circuit with impedances the same way as I handled a similar DC circuit with resistances, I should be able to apply a voltage divider. It says if all I want is the output voltage and I know the input voltage, I can handle it this way. V out is equal to a fraction of the input, and that fraction is given by the impedance of this block divided by the sum of these two impedances. That's strictly analogous to taking R2 divided by R1 plus R2 in our resistor circuit. Just have to be careful with the J's. Okay. Then the usual form for these frequency response problems is to divide the output by the input. So let's take V out divided by Vn. And now work on the algebra inside this parenthesis. I can multiply through top and bottom by j omega c. That leaves me a 1 upstairs divided by 1 plus j omega rc. And in fact, if I notice, this term is dimensionless, so this term had better be dimensionless. And if omega is in units of frequencies, that means rc has to be in units of inverse frequency. And you remember, RC was our time constant for the transient problem related to this, and so that's not surprising. What we can do is define 1 over RC to be defined as a special frequency for this circuit. It happens to be called the cutoff frequency, and we can redefine our problem this way. Plus j omega over omega naught. And now if I looked at the magnitude of this as a function of frequency, what I would find is the following. At very, very low frequency, in fact, if we set omega equal to 0, this term would disappear, and I would have a 1-to-1 match of output versus input. So I start off at 1, and then thinking in terms of just the magnitude, as omega goes very, very large, much, much greater than omega naught, this denominator gets to be huge compared to 1, and the whole thing collapses down to 0 in the limit. As omega goes to infinity, this drops off to 0. And it does so that way, kind of gradually. Omega naught is the value right here, and just from the way we've defined it, it happens to be the point where this amplitude goes down to 1 over square root of 2 of its original value, its DC value. So this gives you an interpretation of this omega naught. It's called the corner frequency because this is roughly where the curve starts to turn around the corner of decreasing amplitude with increasing frequency. But what we have here is a pretty close match to the low-pass ideal. For frequencies much lower than omega naught, we've got a lot of transmission through to the output. For frequencies that are very large compared to omega naught, we've got no output. So what we can do is come back here now and label this as a low-pass RC filter. And in fact, if I wanted to make a high-pass RC filter, I would just have to exchange the roles of capacitor and resistor. And what I would suggest is, as an exercise, you go through and convince yourself that this circuit is a high-pass. And you can go through the same sort of algebra defining this as V out and define this as V in. And that would be a pretty good exercise for you to go through. What you should get is something that looks similar to this. As omega goes to very high frequency, you asymptotically approach 1. And when omega is equal to 0, you get 0 transmission. So that's a little bit about first order filters with capacitors and resistors. We can do the same sort of thing with resistors and inductors. And what I want to do here is just sketch the two filters for you, and again suggest you do as an exercise the phasor derivation of this using the voltage divider. What I'm going to do here is just figure out from high and low frequency limits which one is which. Because right now we can pretend that we don't know which one this is. One of them is low pass and one of them is high pass. I'll tell you that right now. But as to which is which, sometimes you get a little confused, you don't quite remember. It's pretty easy to figure out. What you do is you look at the impedance model for the inductor, and you say Z sub L is directly proportional to frequency. So Z sub L for omega equals 0 is going to be equal to 0. And that means at low frequency I have 0 impedance across this inductor, so I get no output. So low frequency, no output. High frequency, Z sub L when omega goes infinite, actually goes infinite. And so when I'm at high frequency, this impedance is so much bigger than the resistor's impedance that the voltage divider tells me the output is going to be virtually the same as the input. So here we have for this circuit, looking at the inductor's impedance, low frequency gives us low output, high frequency gives us output equal to input, and so there's what my A of omega would look like. This is a high pass, RL. And now, just because I know that these things behave the opposite way when I exchange the roles of R and L, I can just label this as a low pass and sketch its behavior just like that. Now the only question is, where is the corner frequency? Where is the break frequency? And again, recall that in the transient version, the time constant was L over R. Remember, units of henries are volt seconds per amp, and if you divide through by volt per amp, you get a unit of second. So that means that R over L is some kind of frequency, and in fact, that's what we define as the corner frequency for this RL. Now, you can figure that out from looking at the voltage divider and the impedance models, and I suggest you do that just to clear this up. But for one final point, I'd like to show you that if let me put this capacitor high pass back up here. Notice if I go from a capacitor high pass, and let me show it that way. From this circuit to this circuit, the only change I've made is I've replaced a capacitor with an inductor. And I've gone from having a high pass RC to a low pass RL. And that's real useful because all it means is you just have to figure out one of these first order filters. Let's say I write this one out and I figure out it's a high pass. And now I know all the other three, because I know if I switch the R and C, I get a low pass RC. If I replace the capacitor with an inductor, I get a low pass RL. And if I replace and then switch so that there's a resistor up here and an inductor, then that's my high pass RL, just like I showed you here. So for these first order filters, all you really have to do is apply the voltage divider to the first one and then remember all the others just by the arguments I just made. Now, there's one other topic that appeared in the review material that I need to mention along the lines of this frequency response, and that's what happens when you have resistors, capacitors, and inductors all in the same circuit. And the first one to show you is for a series connection. What you get for an input voltage here, and you're looking at the current that goes through. So actually one way to compare volts to volts is to say, well, the voltage across this resistor is proportional to the current through it. But what you'll find is that for very low frequencies, let's actually recall what the capacitor and inductor look like in their impedance models. Okay, if the frequency is extremely small, then the capacitor impedance is going to be huge and the current will suffer. It'll be a very low current for that reason. If I have a very high frequency, the inductor is going to dominate. It's going to make the equivalent impedance here very large and the current's going to be very small. So there's got to be some intermediate frequency where the current is the maximum value it can have. And in fact, you can see that if you plot versus frequency, the magnitude of I of t as a function of frequency, it's going to look something like this. Okay, where at low frequencies the capacitor is blocking the current. At high frequencies it's the inductor that's causing the problem. And boy, did I mess up. That's a capacitor, so it should be a C. And that's an inductor. So there you go. That's not E. Let's block that out. Sorry about that. So when the frequency gets real high, it's the inductor here that's keeping the current from being very large. But somewhere in between, what happens is that the capacitor impedance and the inductor impedance just cancel each other out. You get a ZEQ equal to R plus J omega L. And now if you'll let me put the J upstairs, that makes this a minus J 1 over omega C. Now you can get a hint of what's happening. There's some frequency in the middle of these two extremes, some frequency where this imaginary part just drops out completely. The impedance becomes purely resistive, and the current is a maximum. And that happens when omega L equals 1 over omega C. I of t is going to be maximized. And that happens at a special frequency called the resonant frequency. Omega naught is 1 over the square root of LC. Might be interesting to look at the units for inductance and capacitance and prove to yourself that this has units of radians per second like it's supposed to. Now before we leave that, there's an aspect of this resonance curve, it's called. It says if I look at the half power points, and half power means that I'm looking at 1 over square root of 2 of the magnitude. So if this is normalized to a value of 1, and I go down by a factor of 1 over square root of 2, that defines a range of frequencies over which we have pretty good transmission. If we're looking at this as the current is the output, the voltage is the input, then here's where the output versus input is very large. When you're outside of that band of frequencies, you're losing a lot of current. Well, this range is called the bandwidth, B. And if you have the bandwidth very small, that means that your resonance curve is going to be a very strong spike. If the bandwidth is very large, then this curve is spread out over a lot more frequencies. That's a measure of the quality of the circuit. So there's something called a quality factor, which you'll see in your notes. And we're going to talk about that in just a minute. So as I said, we have this resonant curve, and there's a band in the middle where it's got a very large output versus input ratio. So that range of frequencies is defined as the bandwidth. You have your fixed frequency, omega naught, the resonant frequency, and then there's a measure of the quality of your resonant filter, that's quality factor ratio of the resonant frequency to the bandwidth. Now you think of this as if the bandwidth goes down, the quality of the filter goes up. So here would be a very narrow band filter. And you think of this as, for instance, a radio tuning circuit. You want to tune in the frequency that's right here where there's a radio program broadcasting, and you don't want the broadcast from this channel or this station over here. You want that bandwidth to be very narrow for that tunability. So you need a high quality filter and you need a high quality factor. Now if your quality factor is lower, then you're going to get a much wider band at the same resonant frequency. Let's say this omega naught is the same for both. And in this case, if you have stations broadcasting at this omega naught and this frequency and that frequency, this is a pretty poor job of selecting that station. So that's where the idea of the quality factor comes in. For a series resonant circuit, the quality factor reads omega naught L over R. Now we can have the same sort of arrangement of parallel connections, and all you have to do is imagine connecting resistor, in fact I'll sketch it here, resistor, capacitor, and inductor all in parallel, perform this same resonance function. So you're comparing the voltage applied across these nodes to the amount of current going through it. It'll have the same resonant behavior. The only thing is the quality factor changes. We can use the units to help us remember. It's always quality factor is proportional to omega naught. That's the first thing to remember. But now, looking back up at this definition, omega naught's in radians per second, bandwidth is in radians per second. So this is a dimensionless ratio. So we need to make this dimensionless. How did we get it here? Omega naught is in inverse seconds, L over R is in seconds. If we have the parallel, it's the other time constant that comes in, RC. And it's handy to me to remember that you've got to make this dimensionless, so it's omega naught is in inverse seconds, RC is in units of seconds. That's what the quality factor would look like for a parallel resonant. Now we're finished talking about the fundamentals of DC and AC circuits and transients. I want to finish up with a description of a very important electronics device called the operational amplifier. I want to remind you of what the ideal model is and show you briefly where that ideal model comes from, and then go through a few examples of how you can create useful amplifier circuits with an operational amplifier. But starting off with the definition, an op-amp stands for operational amplifier, and sorry about that. That's what I wanted to show you first. It's page 1. So starting at the beginning, which is usually a good idea, An operational amplifier is summarized by the phrase op-amp. Now, what an op-amp can do for you is take an input signal and amplify it, but where this is most useful is taking the difference between two input signals and amplifying that difference with a magnitude of A, called a voltage gain, and it's not accidental that this is the same letter we used for our frequency response. Vout divided by Vn was also called A. This A is called the open loop gain, and the equation relating the output to the inputs is what you see here. This is the equation that you would use in very detailed calculations using real op-amps and very thorough analysis. What I'm going to show you next is a simplified version of that, which actually is very powerful and very useful for even a lot of electrical engineering applications. The ideal model is good enough. So what I want to do is show you how that more realistic gain model turns into an ideal model. What you need is a voltage gain of infinity, which obviously, if you think about that practically, that's not achievable, but we can get very close to it with a well-designed integrated circuit package. So let's suppose for a moment that we can let the open loop gain go to infinity. See what our equation becomes from the previous slide. You just divide through by A on both sides and then let A go infinite, and that means that Vout over A, if Vout is a finite number and A goes infinite, that difference between the inputs goes to 0. So this peculiar looking situation occurs. In the ideal op-amp, you've got the two input voltages are identical, and that difference of V1 minus V1 minus V2 equals 0, that 0 effectively is multiplied by an infinity to give you a finite answer. So it seems fairly bizarre when I say it that way. The way to rationalize it is to remember this ideal op-amp is really just a useful approximation. It's a real close approximation to the way a real op-amp works. In a real op-amp, what you would have is a potential difference of about a microvolt across these two, and a gain of 10 to the 4th or 10 to the 5th volts per volt. So what you get out here is on the order of a volt or a fraction of a volt, much, much bigger than that tiny little difference. And the difference between these two is so much smaller than all the other voltages in the circuit that we can effectively assume that it's equal to 0 and get pretty good results. There's a related limit. It's not, we don't have time to show it right here, but it has to do with another internal parameter of the op-amp called the input resistance. If you drew a resistor between these two nodes and then allowed that resistor value to go infinite, that would be the same, essentially the same limit as making the gain go infinite. What that says is that there can't be any current in these wires. So if we have an infinite input resistance, no current in these wires. So now, to summarize, what I want to remind you of about the ideal model is that V1 equals V2, where those represent the input signal voltages, and that the currents going into those inputs are both 0. Now, coupled with the Kirchhoff laws and the node voltage technique, we can use these two parts of the ideal model, attach a variety of external resistors in resistor networks, and come up with some really very useful applied circuits. So I think what you'll appreciate from this next slide is where the op-amp gets its name, and also why it's a useful thing to know about for all engineers. The op-amp can be used as an amplifier that inverts the output with respect to the input. You can make an amplifier that doesn't invert and doesn't cause that 180-degree phase shift. You can take several input signals and add them together with different coefficients. So you can do a weighted sum of inputs. That's called a summing amplifier. You can take the difference of two inputs and amplify that. For control purposes, this is a very useful circuit. It allows one of the inputs to be a set point for a thermostat, for instance, and the other input voltage is a measured voltage from a thermocouple. And so you can have the op-amp circuit creating an output voltage that's either positive or negative depending on whether the temperature is higher or lower than you want it to be. And that has very useful applications in instrumentation. For signal processing, sometimes we want to have the integral of the input signal or the derivative of the input signal, and that's where these circuits called integrator and differentiator come in. So now what I want to do is take you through a couple of examples. We have time for about 3 of these to show you how to use this ideal model to figure out some of the circuit problems involving op amps that you might see on the exam. So let's start off with the inverting amplifier. If you only have time to really study and understand one op amp circuit, this is the one to do, because everything else is based on this basic layout. What we're doing is tying one of the inputs to ground, so this is 0 volts, and this is our input, so let's call that Vin, and this is V out. Now I'm going to go ahead and use lowercase letters because this op amp works very well for AC signals. It works for any time-dependent signal, and in fact, as a subset, if the frequency goes to 0, that becomes a DC current, and these work very well as DC circuits as well. What I'm doing is bringing the input voltage into the op amp through a resistor R1, and then resistor R2 is allowing a portion of the output to feed back into the input. So this you'll also sometimes see called RF, F for feedback. But the way we're going to figure out how the output relates to the input is simply to apply the ideal model of the op amp and the Kirchhoff laws. So let's call this I1 and I2. Remember what I said about the ideal model? The current in this wire is 0. And that in reality would be a few microamps, but compared to the milliamp level currents, it's so much smaller in a real circuit than the other currents in the circuit that we can effectively approximate it as 0. But for ideal model calculations, you just go ahead and assign 0 current to that wire and 0 potential difference across the inputs. Remember, these are the ones that I was calling V1 and V2 in the other drawing. So now we can say, ideal model says V plus equals V minus if those are the node voltages at the negative and positive inputs. We've already included the 0 current. So now, Kirchhoff current law. KCL says I1 is coming in, and we have leaving 0 amps plus I2. And now we need to translate these currents into their node voltage expressions. The current I1 is going through resistor R1, and the voltages at the two ends of that resistor are Vn and 0. So let's put that in the equation. Vn minus 0 divided by R1 equals, don't have to worry about the 0 anymore. The I2 current is between the node 0 volts and V out. So I2 is 0 minus V out divided by R2. Some trivial algebra, and you get minus R2 over R1 times Vn. What this says is that the output voltage is a multiple of the input voltage. That multiple can be positive, well, it's got to be negative. It can be larger than 1 or less than 1. It's always going to be negative because of this minus sign, and that's why it's called an inverting amplifier. For instance, if this were an AC input signal that looks like this, if Vn oscillates this way with respect to time, V out is going to be inverted in phase, and so it starts off here and has its maximum where the other has its minimum, and so on. But you can make this ratio whatever you want. That's probably, as I said, the most important thing for you to remember about the op amp circuit, because what we can also do is substitute impedances for resistances, and we can have RLC combinations here, RLC combinations here, and to figure out the output versus input, you just make these phasors, and make these impedances and use the same basic layout. Well, next circuit I want to show you is the non-inverting amplifier. This time, instead of grounding the positive terminal, I'm going to bring my input signal into the positive terminal. So there's Vn. I'm going to have my same resistor ratio or resistor network, R1 and R2. And there's my feedback path again through R2. What I need to do with this terminal is ground it. And now let's go through, since the analysis is very similar to what we had before, we'll just go through and start off with the description that I1 has to be equal to I2, again because the current in this wire is 0. If V plus equals V minus and V plus is at the input voltage Vn, that means that this wire, this node, is at Vn. So I can write 0 minus Vn divided by R1 equals Vn minus V out divided by R2. And now when I collect my terms and rewrite this, 1 plus R2 over R1 times Vn. This tells me again the output is a multiple of the input, but notice that this multiple is always going to be positive. So now we have an output and input that are in phase with each other. It's not inverting the output. And in some instances, that's a useful thing. Well, as one last example, let me show you the op-amp integrator and where it comes from. Notice that I'm involving the same basic layout as for the inverting amplifier. So one thing that we can expect is probably the output is going to be inverted with respect to the input. But the way we're going to decipher this problem is, again, just using the linear model for the capacitor and the ideal model for the op-amp. We've got 0 volts at this node and therefore 0 volts at this node. I1 equals I2. I1 is the potential difference divided by the resistance, Vn minus 0 divided by R. Now, for the capacitor current, we've got a linear model that says I is equal to C dV dt. We have to be careful with our passive sign convention, so let's say that this is the polarity we're assigning to the capacitor voltage, and that means we're assuming the 0 volt node is at a higher potential than the output. It doesn't really matter whether it truly is at a higher potential or not, as long as we set up a convention and we stay consistent with that. So this polarity symbol allows us to write down C d by dt of V sub C. And it's very important to keep track of these minus signs, because now V sub C in terms of node voltages is 0 minus V out. And so that tells us that we have a Vn divided by Rc is equal to the minus time derivative of the output. What you usually do is express these in terms of output equals function of input. So let's just integrate on both sides, and we get V out is equal to minus 1 over Rc times the integral of the input. So we have an output voltage that's the integral of the input voltage. So if we put in a square wave here, we get a triangle wave out. It's very useful for signal processing. And you just have to keep track of this minus sign and remember the factor of 1 over Rc. There's a similar result you can get by exchanging the roles of resistor and capacitor. You can get a differentiator. And I'll just show you that circuit here on this sheet and let you figure that one out as an exercise. I think you'll actually see this result in your reference manual. And it's another example of the analogies between these circuits. You notice the difference between this one and this one is I've just exchanged the roles of resistor and capacitor. And so where in this circuit I have the output is proportional to the integral of the input, for this circuit the output is proportional to the derivative of the input. Wanted to show you the references that I used. I guess I showed them to you briefly at the beginning. There's a description of these books. The first one is the reference handbook, similar to the one you're going to be allowed to use in the exam. Second reference is the EIT review manual that I believe you have copies of. Now the third one, I'm just giving you the bibliography data, just the author and title of this book. It's a thorough textbook for an entire survey of electrical engineering, and so it contains a whole lot more than you would want to study for this exam. The reason I mentioned it is, for one thing, this is the book we use at Texas A&M for our circuits course for non-majors. At your university, you probably used a similar textbook, and I would encourage you to go back to that book for some of the details and additional problems to look at. Finally, my contact information on this sheet. Between now, the time you view this tape, and the time you come to the live session, if you have questions about what I've covered, or if you would just like to call up and talk about electrical engineering in general, I'd be happy to talk with you by telephone, or you can send an email to my address as shown there. I wish you good luck on your exam, and I look forward to seeing you in a few weeks when it's time for the live session. Thank you.